Okay, so in this video we're going to be beginning our integration topic. So integration or antidifferentiation is the process of finding a function from its derivative. So it is reversing the differentiation process, as the word antidifferentiation suggests. There's quite a lot of notation around antiderivative, and it's really important to get it right. It's something that the VCA examiners mention in their report every year, and you will lose marks for not using correct notation. I marked some methods trial exams during the holidays, and I sent my Year 12 class an email after I'd marked page 1 to remind them of notation. So let's sort of try and get this right, make it a focus of your work right from the beginning, and you'll find you just don't even think about it. You know, I just don't even think about what I write. I just do it because it's so ingrained, and it's so important that you start that from the beginning and that you make sure you pay attention to detail, to notation throughout, so that you get things right. Okay, so the notation that we use is this is the integral symbol. Okay, I would read that as the integral of, or the antiderivative of, f of x, and this is what you'll forget, and that is that we are antidifferentiating with respect to x. X is the variable in the expression that we are antidifferentiating with respect to. In the same way that when we write derivative, we differentiate y with respect to x. It's the x variable that we're differentiating with respect to. If this was a function of t, then it would be dt. Okay, so the key thing is that this integral symbol and this dx, they go together. Okay, they don't go anywhere without each other. They are like the world's most inseparable couple that you never see alone. Okay, you never, ever, 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 under any circumstance, write that symbol without there being a d something after it. Okay, so it's really important not to forget that it'll be dx's that you leave off all over the place. So when we find the antiderivative of f of x with respect to x, or the integral of f of x with respect to x, we can sometimes, it's not super common notation, but we can sometimes refer to that as capital F of x. So the antiderivative of f of x being capital F of x. And so that means if we have f of x, when we differentiate, we get f dash x. When we antidifferentiate, we get the antiderivative capital F of x. Okay, but that also means if we have the antiderivative and we want to get back to the original function, we're going to differentiate. Or if we have the derivative and we want to get to the original function, we need to antidifferentiate. So we're going to antidifferentiate in that direction and differentiate in that direction. Okay, let's think about the polynomial functions below. So we're going to establish our rules for antiderivative by thinking about what we know about derivative. Okay, so let's calculate the derivative for each of the following polynomial functions. So if f of x is equal to x squared, then f dash x, the derivative, and I know we've had a holiday in between, so let's refresh our memory. Remember, if we're differentiating x to the power of n, we do n times x to the power of n minus 1. So if it's x squared, it'll be 2 times x to the power of 1, so just 2x. Okay, derivative of x squared plus 1. Okay, so remember, 1 is essentially x to the power of 0. So when you antidifferentiate that, you get 0 times x to the negative 1, so you just get 0. So differentiating a constant, you always get 0. And that's also having an understanding of gradient function. If we've got y equals a constant, the derivative of that, the gradient of that, is always going to be 0. Okay. So x squared plus 1, the derivative of x squared is 2x, and the derivative of 1 is 0, so it'll just be 2x. If our original function is x squared plus 24, the derivative of x squared will be 2x, and the derivative of 24 is 0. X squared minus 5, the derivative of x squared is 2x, and the derivative of negative 5 is 0. X squared minus 56x, derivative of x squared is 2x, derivative of the constant is 0. So this presents us with a problem, given that what we're looking at doing is being able to antidifferentiate. So we want to be able to know, okay, if we have 2x, what's its antiderivative? And what we're seeing here is that whilst we'll be able to work out that there's going to be an x squared involved, what we're not going to know is whether or not there is a constant value and how big that constant value is, because in the process of differentiating, it becomes 0 and it disappears, and so therefore to try and recreate it is impossible without further information. Okay, and we'll look more about that next lesson. So what we've learnt here is that the antiderivative of 2x is clearly going to be x squared, but there could also have been some kind of constant value, okay? Where c is a constant. So it could be any real number. Fraction, decimal, positive, negative, we don't know how big it is. So we don't usually write this, but we must always write plus c when we find an antiderivative. We'll talk more about situations where we don't need to worry about the plus c, and there's a few situations down the track. But for now, every time we antidifferentiate, we must always include a plus c. And this was the email that I sent to my Year 12 Methods students, who all lost at least 1 out of 2 marks in the first question because they failed to write plus c's on their antiderivatives. Okay. So let's see if we can generalize this then. So we know, again, let's work from what do we know about differentiating, and then let's think about reversing that in order to antidifferentiate. So we know that when we differentiate x to the power of n, I just wrote that up there earlier, we do n times x to the power of n minus 1. So the first thing we do, so let's note clearly what the 2 steps that we do in order to differentiate are. The first thing we do is we multiply by the power. And then, after we've multiplied by the power, which is n, we then subtract 1 from the power. That order is really important. If we subtracted 1 from the power and then multiplied by the power, we'd be multiplying by n minus 1. So the power stays at n, we multiply by that, and then after that we subtract 1 from the power. I can't say other words and then write something different at the same time. Multitasking. Okay, so multiply by the power and then subtract 1 from the power. Okay, so to antidifferentiate, we want to reverse this process. Okay, so that is doing the opposite thing, but not just the opposite thing, but also doing the opposite thing in the reverse order to reverse the process. So the first thing we would need to undo is the subtracting 1 from the power, and the opposite of subtracting 1 from the power will be to add 1 to the power. And then after we've added 1 to the power, we're going to do the opposite of multiplying by the power, which is to divide by the power. And it'll be, because we're doing it after we've added 1 to the power, we'll be dividing by that new power. So we'll be dividing by n plus 1. Okay, so antidifferentiating, let's summarize that here then. So the antiderivative of x to the power of n, we're going to add 1 to the power, so it'll be x to the power of n plus 1. And then divide by that new power. Okay. The other way we could write that, that's the same as saying 1 on n plus 1 times x to the n plus 1. Okay, so sometimes it's neater to write it that way, sometimes it's neater to write it that way. And don't forget, plus c. Now, the one thing to note is that this rule only applies where n is anything other than negative 1. If we were to think about what would happen in those instances, if we were integrating x to the power of negative 1, we add 1 to the power, which negative 1 plus 1 is 0, and then we divide by the new power, which is 0, and obviously we've got this big alarm bell situation that we're dividing by 0. So the antiderivative of 1 on x does, oh sorry, got my highlighter still. The antiderivative of x to the negative 1, which is 1 on x, does not follow this pattern, okay? It actually gives us a logarithm, but we won't worry about that until next year. So we'll only be dealing with antiderivatives of x to the power of n where n is a number other than 1. Okay, so let's think about if we had the antiderivative, so I'm here now, the antiderivative of x to the power of 4, so that is going to be x to the power of add 1 to that power, which is 5, and divide by that power, which is dividing by 5, plus c. Or we could write that as instead 1/5 times x to the power of 5. They're the same thing. Plus c. Okay. Some other properties of integrals that we need to understand. Now, these are things that we tend to, once we sort of have a sense of them, we just do them intuitively. We don't write out lots of steps here. I'm going to write out the steps once here to show you how these apply, but generally we just kind of do them. But equally, there are many situations where it's important to sort of understand that this is how integrals work. So the first thing is that if we are adding or subtracting 2 functions, so that could be as simple as the integral of x squared plus the integral of x cubed. Sorry, the integral of x squared plus x cubed, okay, or minus. Then we can simply just integrate those 2 things separately, okay, so it's just going to be the integral of the first function of x, so in this case that would just be the integral of x squared with respect to x, plus the integral of x cubed with respect to x. So we just integrate each part separately. So as long as we've just got addition and subtraction, we just integrate each bit separately or anti-differentiate each bit separately. And that's true for when we're differentiating as well. We know if we're adding or subtracting terms, we simply just differentiate each term. Now, I wouldn't write out this step. I would simply just immediately differentiate each of those terms separately. Sorry, anti-differentiate. So the antiderivative of x squared would become x cubed on 3 plus the antiderivative of x cubed would become x to the 4 on 4 and then our plus c. But what we're really doing is essentially just anti-differentiating each part separately. The key thing that's missing from there, and this is the same problem that we had with differentiation, is that we should note that if we are anti-differentiating f of x times g of x, it is not the antiderivative of f of x times the antiderivative of g of x. So if it's a product of two functions, we cannot just differentiate each part of the product separately, anti-differentiate each part of the product separately. We must first simplify or expand so we've only got addition and subtraction. Similarly, if it was division, okay, it is not just the two separate integrals divided, okay. So it's really important that we're careful about that. So you just need to make sure that you manipulate whatever you're trying to anti-differentiate so that you just have terms involving x being added and subtracted, okay? The next key thing is that if we have a number times f of x, we're integrating a number times f of x, so that could be as simple as having 3 times x to the power of 4, okay, with respect to x. So essentially the key is that this number doesn't actually have any impact on how we anti-differentiate. We're still just anti-differentiating the function of x, so x to the power of 4, and we're multiplying that by 3 after we've done that antiderivative. So we can think about this as we can essentially just take that 3 out of the integral, so it's the same as 3 times the integral of x to the power of 4, and so it is 3 times x to the power of 5 on 5, and so that means it is 3/5 times x to the power of 5, or we can write it as 3x to the 5 on 5, same thing, okay? So obviously if this number here was, 10, then that would simplify quite nicely, because you're going to have 10 on 5, which is 2x to the power of 5. So again, I wouldn't bother to write out this separate step. I wouldn't bother to take that number out. I would just do it. I would add 1 to this power and then divide 10 by 5. Great. But the key is that the 10's not changing how you're anti-differentiating the function of x. You're just still getting 10 times the antiderivative of your function. Okay. And again, there are places down the track where it's helpful to understand that you can take that number out of the integral, but I certainly wouldn't be taking them out of the integrals as a matter of course. I would just do the integration. So something like this, I would pretty much go straight to my answer. Okay. Might need one line to simplify, but to be clear about what's actually happening, given that we're only adding and subtracting all the terms, we can split them up into 3 separate integrals. We're integrating 3x squared with respect to x, then we're subtracting and integrating 4x with respect to x, and then we're adding and integrating 5 with respect to x. Now the other thing to think about is that 5, a constant value, is 5x to the power of 0. So if we're anti-differentiating 5x to the power of 0, the 5 can come out the front. We add 1 to the power, which makes it 1, and divide by that new power. So we get 5x. And that should make sense if you think about differentiating. Differentiating 5x, you get 5, hence anti-differentiating 5, you'll get 5x. So if you're anti-differentiating a constant value, you just add x, okay, as long as you're anti-differentiating with respect to x. So the first thing is that we're anti-differentiating 3 separate terms, and we can just think about them as 3 separate antiderivatives. As I said, I wouldn't write this line out, I would just be doing that in my head. The other thing to think about is that the constant terms don't affect the antiderivative. So the 3, we're essentially just anti-differentiating x squared and multiplying that answer by 3. We're essentially just anti-differentiating x and multiplying that answer by 4. And we're essentially just anti-differentiating x to the 0 and multiplying that answer by 4. Okay, so that's essentially what we're doing here. The antiderivative of x squared is x cubed on 3. The antiderivative of x, which is x to the 1, is x squared on 2, and the antiderivative of x to the 0 is x to the 1 on 1. Okay, so we've essentially just got, in this case, the 3 will cancel down with the third that we got from the integration. Okay, so that would just be x cubed. In this case, the 4 and the 2 will simplify to give us 2x squared, and here obviously we're just going to have 5x. So as I said, that's a lot of extra steps that I wouldn't be writing out, okay, but I'm just being clear about that these properties are what we're essentially executing, okay, and the key is that these properties work, but if it's multiplication, all of a sudden it doesn't work, okay. If it's division, all of a sudden it doesn't work, okay. And it doesn't just have to be multiplying by a number. Obviously you could have antiderivative of x to the power of 5 on 7, okay, dividing by 7, but that's the same as division's the same as multiplication. It's multiplying by 1/7. So you could take out the 1/7 if you want, then antidifferentiate x to the power of 5, which would be x to the 6 on 6, and then you can multiply them back together, which would be x to the 6 on 42. But I wouldn't bother to take it out, I would just do that all at once. So right back here, I would think, okay, well I'm going to be adding 1 to the power and dividing by 6, so I'll have 7 times 6 on the bottom here, so that's going to be x to the 6 on 42. Plus c, plus c, plus c, plus c. As you're working through, you can just stick your plus c on the end at the last line, but don't forget to include it. Alright, let's work through some antiderivatives. So antiderivative of x cubed plus 4. So we want to think about, we're essentially antidifferentiating x cubed and then separately antidifferentiating 4, but I'm not going to write out that line, we just do them separately. So antiderivative of x cubed is going to be x to the power of 4 on 4, and then we'll have plus antiderivative of 4, which is going to be 4x, and then plus c, and we're done. You can write that x to the 4 on 4 as 1/4 x to the power of 4 if you prefer. Okay, example 2 here, we've got a product, okay, we've got x cubed times 3x squared plus 8, okay, and so we cannot just, it's not just antidifferentiating that and then separately antidifferentiating that, we must expand it out first, so we only have addition and subtraction involved in our expression. And again, notation, we haven't antidifferentiated yet, so it's still going to be equal to the antiderivative of, this will be 3 times x to the power of 5 when we expand that, plus 8 times x cubed, and we need to antidifferentiate that with respect to x, okay? And so now that we're going to take the antiderivative, we lose our now that we're actually antidifferentiating, we're not going to write that we're still antidifferentiating something because we have antidifferentiated. So 3, we add 1 to the power, becomes 6, and divide by 6. So notice I don't bother to take the 3 out, I just leave it there. Plus this will be 8x to the power of 4, and we divide by 4. But the point is it hasn't changed how we antidifferentiate x cubed. It's still x cubed becomes x to the 4 on 4, and we're still multiplying that by 8. And we'll have plus c. Let's just simplify those fractions. So the 3 on 6 becomes just 1 on 2, so it's x to the 6 on 2. 8 on 4 becomes 2, so that's 2x to the 4 and plus c. And again, you could write this as half x to the 6 if you prefer. You can take the fraction out separately, that's fine. Okay, question 3. We've got 3x squared plus 4x to the negative 2 plus 3. Okay, so antiderivative, again, just sort of thinking about doing each term one at a time, but I wouldn't bother to write out a separate step of the 3 separate integrals. 3x squared is going to become 3x cubed divided by 3 plus 4x to the negative 2 is going to be 4x. Adding 1 onto negative 2 is negative 1 divided by negative 1, and then plus 3, thinking about that's 3x to the 0, so it becomes 3x to the 1 on 1, so it's just 3x. Or it's just thinking about reversing the differentiation process. Derivative of 3x is 3, antiderivative of 3 is 3x. And then plus c. Let's just tidy up our fractions, so 3 on 3 is just 1, so it's x cubed. And that's going to be 4 divided by negative 1 is just negative 4, x to the negative 1, plus 3x plus c. You can, of course, write that back as 4 on x if you prefer, but the original expression had negative powers in it, so I'm happy to leave it with negative powers. Okay, and then example 4 here, we've got a quotient or division of two functions, okay? So we cannot just antidifferentiate the numerator and antidifferentiate the denominator. We must simplify it first, okay? The easiest way to simplify these fractions, I recall when we did differentiation, a lot of you spend a lot of time mucking around with negative powers. Just think about splitting this as two separate fractions. This is the same as 2x on x squared plus x to the 5 on x squared. It's just simple fraction, reversing. Common denominator, you put them together. Similarly, you can break them apart, okay? So let's simplify each of those. Again, we haven't antidifferentiated yet. We're still just simplifying the expression, so we're still carrying our derivative notation until we take the antiderivative. Okay, so that's x to the 1 divided by x squared, so subtracting those powers, that's going to be 2x to the negative 1. Ah, that's a problem. My apologies, because... Oh no, that's okay. Ah, no, that is a problem. My apologies. Let's change the original question. Let's make it on x cubed. Okay? So let's make that power on the denominator cubed instead. Sorry, that's my fault. So now when we subtract the power, that'll be 2x to the negative 2. Okay? And then this will be plus x to the 5 on x cubed is just x squared. Okay, so we haven't done any anti-differentiating. All we've done is simplify the expression to a point where we've only got addition and subtraction between terms. Any multiplication is just multiplication by a number. That's fine. It's not multiplication of two functions. And now we can anti-differentiate each part separately. So it's going to be 2x, and then we add 1 to negative 2, which is negative 1, and divide by that power, which is still negative 1, plus x squared becomes x cubed divided by 3, and then plus c. 2 divided by negative 1 is just negative 2, so it's negative 2x to the negative 1 plus x cubed on 3. There's obviously lots of different ways that you could write that. This is obviously negative 2 on x plus x cubed on 3 plus c. Or if you've got a common denominator there, it'd be negative 6 plus x to the 4 over 3x plus c. Okay, all of these are fine. There's none are more simple than the other, just different ways of writing the same thing. Make sure fractions are in simplest form, so don't leave it as 2 over 4, make sure it becomes a half, but otherwise you don't need to rewrite it back with a common denominator or anything like that. Okay, anti-differentiating using your CAS. So you might recall the number of different ways that we can differentiate with our CAS. All of those methods still apply. So menu for... There's a calculus menu. We use derivatives, options 1 and 2, but obviously you've got number 3, integral, would allow you to anti-differentiate. You can also go to the template palette, which is the button next to number 9, okay, and there should be an antiderivative template here. You get two versions here actually. You get the one that you just saw that came up before that looks like that, or you actually here also get this one, which doesn't have those little boxes. We'll talk about those little boxes down the track, but for now, just finding an antiderivative, you don't need those little boxes next to the integral symbol, so you could just go with this symbol here. And the other way is, you might recall when we're differentiating, shift minus allows us to bring up the derivative template very quickly, and so shift plus brings up the antiderivative template very quickly. So I tend to use shift plus. As I said, for now, those two little boxes that are actually, you see how they're greyed out, so that means they're optional. You don't need to put stuff in there, and for now we won't be putting anything in there. So you could, enter in an expression, let's say x to the power of 6 minus 5x squared, squared, plus 7, for example, with respect to x, and press enter, and it will work that out for you. Your CAS won't include the plus c on an antiderivative, so you must make sure that you remember to add the plus c in yourself. Okay, so the work today is just question 1 from exercise 17E, and then there's an additional worksheet on antiderivatives.